Hello everyone. So we are back again to our plasma class. What we are dealing these days that we are handling the various moments of plasma kinetic equation. We are dealing with the zeroth order moment of plasma kinetic equation, and we obtained what we obtained. We obtained the species conservation equation and the current continuity equation. Now, what we are now going to do in this class, we are going to take the first order moment of plasma kinetic equation, and as we already told that we will be getting the momentum conservation equation from this first order moment. So let us try how it goes. So we start with the plasma kinetic equation. So this is nothing but you just remove this highlighted V's in this. So that is nothing but the your plasma kinetic equation for the including the collision term. Okay. So when you want to take the first order moment, you multiply by this V over here, multiply every term with V and do this integration. So this was the V dot grad x term, this is A dot grad B term, and this is the collision term. Now, to get this integration done, we have to handle all these terms. So how many terms are there? So this term we name index as 1, this is 2, this is 3, this is 4, and this is 5. So we'll handle all this term one by one. And I promise you that we'll be finally getting to a conservation equation which will look like this one. So I just want to assure you that we'll be at the end we'll be getting some expression which is easily tractable. Rather, we will be simplify this further and we will be getting a very elegant and compact form this momentum conservation equation which we can handle in a much easier manner. Okay. So now you know that this first term what it gives you the integration dv and then v into fs xpt. So we'll get that as per our definition of the center of mass fluid velocity vs, this will be nothing but nsvs, and we'll get this term as ms del dt of nsvs. Similarly, the second term you can see that we are getting some average value. This is v into v, and we will be getting this vv. This is basically a tensor quantity which will be coming there, and this one will be giving you ns into q into e, and the last one will give you q ns vs cross b, and then the last quantity. So this is the your rate of change of momentum that will be giving you this quantity when you multiply by v and integrate, and that will not be 0, and we will be putting that as ks. So this term will always appear as the most difficult part to tackle, but physicists always have some way or other to make the things simpler, and we'll apply our tools, our physics concepts to handle this collision term. Okay. So in fluid model, this collision term plays a very important role, and it is all the way. Sometimes we are not able to handle this term, so we need to go for some model of the phenomena, so we can model this term and get some useful expression which we can tackle in a much easier manner. So let us start. So we start with the term 1. So which is the term 1? This one. So del LD of dBV Fs xpt. So this is the term, and we know that by definition this is the expression for center of mass fluid velocity Vs xt is equal to at location x at time t. This is the fluid velocity. This is equal to 1 by ns dv v fs xbt. So you are integrating over all the velocity, and you are getting the velocity, center of velocity at the your coordinate space xt. So we are now interested in the this integration, and this is giving you nothing but ns into vs xt. So the term 1 which we had, we are able to get the value as ns vs xt, and we will put that in that. So we get it ns vs and then del t, and you will see that there was ms was there because we have divided everything by ms. So this ms, when you multiply over here, this ms goes over here and this ms stands there, so that you get the expression like this, and ms get removed from these expressions, and this one, this terms and these terms, and you get ms multiply over here and here, and this ms is coming here, and nsbs as we have seen here, so it is coming from there. Okay, nsbs. Now term 2. So term 2 handling this is dv vv and then grad x fs of xpt. So this is basically giving you in the same way as you have got this v average 1 over here, here you get vv average. So this vv average, this quantity is basically a tensor quantity having the components vx vx, vx vy, then vx vz, then vy vx, vy vy, vy vz, and vz vx, vz vy, and vz vz. So the diagonal terms consists of this vx square, vy square, and vz square, and this off diagonal terms, they are like vx vy and vy vx, and vx vz and vz vx, and vz vy and vy vz. Now you know that we need to simplify the things. So we want to come over here that when a particle is moving in a direction x, terms having the components vx vx presents the momentum transfer in the direction of the motion. So here this is the px term. So it presents the momentum transfer in the direction of the motion. Now the terms associated with vx vy or vy vx or vz vx, they present the momentum transfer in pyx and pzx respectively, like this one. So if it is like this, and then they are the momentum transfer in the orthogonal directions actually. So now when this happens, actually this happens when the viscosity plays the role, because when you are moving in one direction, the adjacent layers, you are imparting some momentum there. So this can well be approximated as 0 when you are considering plasma and assuming that it is having you call that very small viscosity. So compared to other terms, you can neglect that term. So to a fast approximation, we can consider that pxy will be same as pyx, and all these cost terms will put as 0, and we will assume that pxs, payy and pzz, they will be equal with the scalar pressure ps. So we will model it in a bit detail later on. So what we are planning that we will be putting these quantities as 0, assuming that the plasma is having very small viscosity, and to a fast approximation we can approximate this VB tensor as like this. So it is having some diagonal terms, and we are taking that Vx square is same as Vy square is same as Vz square, and that we are assuming as equal to Vs square. So that is the square of thermal speed of species S. So we can write this as Vs square and this tensor like this. Now we are using the divergence of a tensor rule like this, and if we apply the same thing over this VB tensor, then we are applying this like this, and then we are getting this gradient of Ns Vs square. Now the pressure P, you know that P equal to NKT, we all know from our thermodynamics classes or statistical mechanics classes. So Ps is equal to Ns KTs. K is the Boltzmann constant. And what we can do that we are equating that with Kt equal to msv square. So this is the thermal energy, and we are equating with that speed like this. So Kt is the thermal energy, and that is msvs square. So we did this same thing in our previous classes as well, that we compared half of msvs square, that is the kinetic energy, equated with the half Kt, that is equal to thermal energy. So Kts and msvs square, they are written in an exchange. We exchange this two with each other, and we write then that ms vs square, ns into vs square, you come over here, and ms goes this side, so ns vs square becomes ps by ms. Okay, so what we can do that we can write Vb equal to your this thing is equal to this ps comes over here, so nsv square, and we put over here, so this becomes grad ps and divided by ms. So this tensor quantity, when evaluated, we get divergence of ns bs ps is equal to grad ps by ms, grad ps by ms. So this is a case when you assume that the plasma is stationary, like you know that this discharge tube, when it is giving light in your room, it may have that plasma which have the components which have electrons and ions which are moving at very high speed, but the plasma as a whole is not moving anywhere, it is there only. Okay, so then what you can say that the net fluid velocity is 0, so v is equal to 0, and then you are getting this thing. But there are cases when this fluid is actually moving. Okay, then the fluid is actually moving. So in that case, this VA, VB, this tensor comes as BS plus BS square I, as it came this time also. Now, so when you go for this divergence of NS BS, you need to take this divergence of this quantity as well, and you will end up with the expression which gives you this divergence of Vs, NS Vs plus Bs dot grad x, NS Vx plus 1 by Ms grad x of Ps. So this term was already there when we assumed that the plasma is stationary. So this was there, grad Ps by Ms. So this is the thing, this is the same thing. And this term is having now, when the plasma is moving, we have this term, these two terms are there, but we assume that plasma is incompressible. Then divergence V term goes and this term becomes 0, and we are left with Vs grad x plus Ns Vx. So these two approximations, when we are assuming that plasma is low viscosity and when we are assuming that plasma is incompressible, so these are approximations only, and in many practical cases we need to really evaluate these terms and include in our expressions, and I will show you in our later classes that how these terms are handled in actual processing plasma systems, and I will show how to tackle these terms. But for the time being, we are assuming that this term is 0, so that we can easily simplify the expressions what we are getting for this momentum conservations. So we move to our next slide. So this is the one uh, the third term means in our we are continuing from our this thing, so this is the third term, so dBVE grad Vs, and the fourth term will be this one, and the fifth term will be this one. We need to model each of them, and just now we have handled this VB term, and we have found that this VB term is giving a tensor which is finally leading to gradient of pressure. So this VB terms is finally giving us gradient of pressure, and in case of moving fluid it is giving some your divergence V terms which can be considered as 0, and in that case we are left with this Vs dot del and then Vs terms, this term alone, and on the right hand side we can evaluate these terms and we will finally see that these terms. So now we will be handling this dBVE grad VFS. So we come back to that. So this is the third term. Now dBVE grad Vs. So we can take E out and we can write this as derivative of these two terms. If you complete the derivatives, we will finally end up with this one. Now you see that when we are taking this integration, then this FV is coming out, and you know that f at both the limits plus minus infinity, it is becoming 0. So this first term becomes 0, and the second term you are integrating f over all velocity space. So that will give us nothing but the number density. So you are left with I is equal to, this is minus E ns. So we are able to handle this expression in a very smart way. Actually you can do this integration component wise, and it will take a number of pages of your notebook to find out this value. You will ultimately end up with the same thing. So this is really a smart way of getting the integration done, and this is the correct value, that's minus E ns. So the third term is evaluated now. Now we are going to the fourth term. So what was that? This dBV V cross B dot grad V F. Now again, if you break into components and do the integration, it will take long time and it will be really a complex kind of thing. Rather, we again go for some smart way. We note that this V cross B I doesn't have any VI component. Okay. So as we did in our earlier cases in earlier class, we have shown that this V cross Bi do not have any Vi component. If so, then we can take that inside. So like this, we can take it inside, and if we have done that, then we can write in this manner. Okay. So what we are getting now? We are getting now this one is having Vf and V cross Bi, it is coming out, and this is giving us 0, and this we are getting as Fv then dV cross B over here. So this is nothing but Vs as per our previous definition. So we are getting this minus Vs cross B. So this term, the term number 4, when integrated, it is giving us minus Vs cross B. Okay. So and in getting this term, we again this whole term comes out, and we know that this F goes to 0 at both plus minus infinity limit of Vi, and then we get this term 0, and we are left with only this term, and this gives us the center of mass fluid velocity. So Vs cross B. So finally, what we are left with? We are left with the terms ms ns del Vs by del T plus ms ns Vs dot del Vs plus grad Ps is equal to Qs ns E plus Vs cross B plus Ks. So this is the expression which we are now having, and the major difficulty that we are finding now in evaluating the term Ks. So you understand that we have evaluated the first term, we got this, we evaluated the second term which resulted in the VB tensor, and that resulted in this two, that GAD-P and MSNS BS dot GAD-PS. So this is basically because of the center of mass fluid velocity BS when the fluid is moving, and this is what is the your GAD-PS term. Okay, so this is the pressure gradient term, and we got this after indicating the third one, and this after indicating the fourth one, and this is on the right side, which is the your collision term. So after doing all this, these are fine, but we are now left with indicating the collision term, which is nothing but ms dv v del fs by del t. So this is what it is giving. It is giving the rate of change of momentum of the fluid of species S due to collision. Now, how to tackle this thing? So this is a bit tricky, and this is not zero anymore as we did for our your species conservation equation. So we need to tackle this thing. But again, there are ways out. You will see that how we are now handling this term and getting some very useful expression out of it, very useful information rather. So inside plasma, we are assuming that this is containing two fluids. One is your electron fluid and one is your ion fluid. So the electrons are continuously colliding with the ions, and because they are more energetic compared to the ions, they are delivering their momentum to the ions, and ions are getting that momentum. So if k is the momentum lost by the electrons, if we represent that by minus ke, the same is gained by the ion fluid, and we equate that as k. Okay. So this case, when we evaluate it for electrons, we write ke as minus k, and when we evaluate the same for ions, we write that as ki, and that is nothing but k. So what we are getting now? MENE for species electrons, del BE by del T here, and then MENE dot del BE plus grad of PE, that is equal to QS QE into NE, then E is coming over here, then VE cross P, and then we are getting minus K for the electrons. Similarly, for ions, we will write this equation as, we will replace S by I, so Mi, then Ni, then del Vi by del T, that is what I have written over here, then Mi, Ni into Vi dot del into Vi, that is what is written here, and then grad Pi here, then Qi Nie plus Vi cross B plus K. Why it is Qk? Why? We have taken that Ki will be K, okay, here as I explained you just a little before. So these are the expression, one for the electrons momentum and another for the ions momentum. Now what we will do, as we did earlier, that we add these equations and try to get some expression which is useful. Here also we will do so. So one thing, these two terms, that MENE V dot del BE, so these are bothering us. Now these are there when the fluid itself is actually moving, but this will not be there when the fluids are not moving. So can we make this term 0 and still get some useful expressions, useful information? Now you know that at this room temperature, molecules in this room are extremely rapidly moving. So for example, you know that average speed of this molecule in this room, this is around say 500 meter per second. So it is around 1800 kilometer per hour. But even though these molecules are moving at so high speed in this room, but really there is no storm, because you know the fluid as a whole, the whole air in this room as a whole is not actually moving. Okay. So to a good approximation, this B is small, but you know that if a fan is moving in this room, we understand that the air is blowing somewhere, but not everywhere. there is really not like any storm anywhere, but the air may be moving. So V is actually not 0, but this V dot grad V term may be quite small. So in those cases, we can neglect this term, and if the fluid is not moving at all, it is completely stationary, then we can take that V is equal to 0. But plasma moves. Like if there is a fan blowing in this room, the air will move. That velocity may not be very high, and that velocity may be quite negligible compared to the speed with which the molecules are moving. You know that an aeroplane which typically moves at a speed of say 800 kilometer per hour, but these molecules are moving at a speed of 1800 kilometer per hour. But compared to that, actually, if you take the velocity of this air in this room, that is really negligible. So that way we can remove the term for some approximation, these terms which are circled in red, and we can write this expression as MENE del V by del T plus grad P is equal to QENE E plus V cross P minus K. So we are just removing this term and rewriting this again over here, and these are the expressions. So we now add them up, and what we get? We get the del T of MENE V plus MINI VI. These two terms we have added. So MENE V plus MINI VI by del T plus grad of PE plus PI, that is coming over here, that is equal to QENE plus QINI into E plus what we are getting, QENE V plus QINI VI in this, and whole is cross B. So we put in this bracket and key, and then the interesting thing is that now the term which was bothering us, that K, is now eliminated. So that is the physicist who does to come out from problem. But what in turn we have got, you see that we are now circumvented the problem of evaluating the collision term. Only we have modeled that what electrons are losing, the ions will be gaining. We have put the taken out the term from electron equation, and we have put the same term in the ion equation, and when we added them, they just vanished. So we are now ended up with an equation which is del T of MENE V plus MINI VI by del T plus grad of P plus Pi, and that is equal to, come over here, so it is QE plus QI and then you multiply by E, and then this is Vi, this V plus Bi cross B. Now as per our definition, so this is nothing but the your center of mass fluid velocity, so rho m into del B del T, and then this gives you P plus Pi. So when we consider the plasma as a combination of two fluids, one is electron fluid and one is ion fluids, so pressure is additive, so this is contributed by the electron fluid component and this is by the ion fluid component. So add them up and you get the total pressure, and then what you are getting, this is QNE plus QINI, it gives you the net charge density, that is multiplied by E, and this is nothing but J, that is the current density, and this is cross B. So what we are getting now, the momentum conservation equation, which is rho m del B del T plus is equal to minus of grad P, this term goes that side, then rho C into E plus, so this is nothing but the current density, right? So J is equal to NeV, and you have added the electrons and ion terms, and you are getting J cross B. Now this is a wonderful equation, and if we go back, we started with this equation, this one. This equation, we were really clueless about what to get out of it and what information is there inside, but finally you see that we have done very simple approximations, and whatever integration we have done, we have done in a smart way. They may be complex integrations, not complex integral. They are your nature is very complex, but we have done in a very smart way. We could do the integrations and we could get the values and put that into integration, made some assumptions, and we found that the momentum conservation equation appears in a very beautiful form as in the red box. So in this class, what we have obtained? We have obtained the expression for momentum conservation equation. So in the next class, we will be going from for another thing, which is generalized Ohm's law. So you are gradually understanding that whatever we are familiar with, like momentum conservation equation. Momentum conservation equation is we are studying since our school days, but in plasma also the same thing is there, but it is appearing in a very meaningful and different way, and which is involving the pressure gradient, which is involving the electric field, which is involving the magnetic field, which is involving the current density. It is bit complex, but we are able to manage a very elegant form of that. Similarly, we are knowing about the Ohm's law since our school days. In plasma also we will be getting some Ohm's law, but that is generalized Ohm's law. So can plasma behaves as your usual Ohm's law? Can give it usual Ohm's law? So all these things we will try to find out in our next class. Okay. So this much now, and we will meet in our next class. Thank you.